Hi everyone, welcome to my channel. This is Mr. Cervone. In today's Do Now, a cone and a sphere have the same volume. Number 1. If the radius of the base of the cone equals to the radius of the sphere, what is the height of the cone? Secondly, if the height is 12 centimeters, what are the surface areas of the cone and the sphere respectively? Okay, so how would you solve the first problem? Well, we know what the volume of a cone is, and we know what the volume of a sphere is, and we just have to set the volumes equal to each other. So let me denote the volume of the cone as V sub cone, which is equal to 1/3 pi r squared times h. The volume of the sphere is equal to 4/3 pi r cubed. As mentioned before, we want to set these two volumes equal to each other, and we can leave both equations or both expressions in the equation in terms of r because they have the same radius. Thus, we get the following equation when we set the volumes equal to each other. So you can already see that we can work on both sides of the equations by first dividing by pi on both sides. Since r is not equal to 0, so I make sure to actually write this down here, r is not equal to 0, we can actually not only divide pi, but we can also divide r squared on both sides, okay? And finally, we can multiply by 3 on both sides. So that leaves us the following equation, that h is equal to 4r. Okay, and that is actually the answer to number 1 here, okay? Because here we're not given any numerical values, so we know that the height of the cone has to be 4 times the radius of the base of the cone, or 4 times the radius of the sphere itself. Okay, so what about number 2? For number 2, we know that the height is 12 centimeter, the height of the cone, obviously. So what we can do is use the h equal to 4r from the previous problem to solve for the radius first. Once we have the radius, then we can find the surface area of the cone and the sphere respectively. Okay, so if we substitute 12 for h and solve for r, we'll obtain a radius of 3, okay? Or 3 centimeters, I shall say. Okay, so now we can use that 3 centimeters to find, first we want to find the surface area of the cone. Okay, so we know that the surface area of the cone is pi rl plus pi r squared. Okay, so you can tell the L is not there. As you remember, L is the slant height of the cone, okay? So basically, let's say you have a cone like this. So let me draw this out, okay? This is the height of the cone. Let's call it h. We know that h in this case is 12 centimeters. We know the radius of the cone. So let me write this here. So r equal to 3 centimeters. And we know that this forms a right triangle. Okay, so how do we find the slant height L? In this case, all we can do is use the Pythagorean theorem in this manner. L is equal to the square root of h squared plus r squared. Then we substitute, and we obtain that L is equal to the square root of 12 squared plus 3 squared, and that is equal to the square root of 153, which is equal to 3 radical 17. Okay, so now we have r, we have L. We can just substitute back into the surface equation of the cone and obtain the surface area. So the surface area of the cone is 9 pi radical 17, okay? Maybe we should write here that that is equal to centimeters squared, okay? And in a similar manner, we can now find the surface area of the sphere, which we learned the day before that is equal to 4 pi r squared. So we just substitute 3 centimeters for the radius, and we obtain a surface area of the sphere to be equal to 36 pi centimeters squared. Okay, so this was the answer to the do now. Now here we're dealing with more than one solid. And as a matter of fact, today's lesson is about combinations of solid or combined solids. So let's first define the word combined solids. What does that entail? What does that mean? And how do we proceed? A combination of solids is a figure which is formed by combining two or more solids. As you can see here in the pictures, we have different real-life applications or real world where you can see different combinations of solids here. For example, a trailer or a tent or an ice cream, or even this figure with a cylinder and a hemisphere on top, which could represent some type of like a water gate or anything like that, where water is being stored on top of the roof. Okay, so hence today's aim is the following. How do we find the volume and surface area of combined solids? So let's look at an example here. Dennis' scoop of ice cream has a radius of 2 centimeters. It rests in a cone that has a radius of radical 3 centimeter at the widest part, and the scoop is tangent to each line containing a slant height of the cone. He eats some of the ice cream and then finds that the remainder of the ice cream can be pushed down to fill the cone exactly. How many cubic centimeters of ice cream did he eat? As you can see here, we have an example of combined solids. As a matter of fact, a cone and a sphere again. This problem seems a little bit more complex, but let's look into more detail here. So the first thing you want to do here in this problem is draw a two-dimensional representation of this three-dimensional problem, as you can see here to the right. So we know what the radius is, so let's draw that in a way such that we can create some type of right triangles. Okay, so this is it if you draw it from a two-dimensional perspective. Let me also label the points here so we can easily refer to them. So the bottom point of vertex, I'm going to call it A. So this I'm going to call B. The center of the sphere, let's call it O. And then we call this point here C, okay? What angle is angle ACB and why? Well, it turns out that this here is a right angle just because we have the vertical line AO and the horizontal line drawn here that is from B to C, and it continues to the other side as well. Okay, so the next thing we want to do here is to label the dimensions, okay? So the radius of the sphere, it says here it's 2, so I'm going to label that in as BO, and then we have radical 3. So that is the distance from B to C is radical 3. Okay, so you can already see here that we can do certain things, okay? We can, for example, figure out the distance from O to C, and then later we'll see how we can apply that, okay? So here, let's say we want to find OC, so let me label that, OC is equal to, so now we're dealing with right triangle BOC. So that means that OC is just the square root of 2 squared minus radical 3, everything squared. And we're going to take the square root of that, okay? So that means that OC is just equal to the square root of 4 minus 3, which is equal to the square root of 1. And we obtain a length from O to C to be 1 centimeters here, okay? So let me label that in, 1 centimeter. Okay, so if you look at the problem here, it says here that Dennis eats some of the ice cream, but then everything melts and goes inside the cone, okay? So basically this cone gets filled up. So in reality, what you want to find is, and let me write this here, that's the goal here, is to find the volume of the sphere minus the volume of the cone, okay? Because think about this. If you subtract the volume from the volume of the cone from the volume of the sphere, you end up with the volume that Dennis was able to eat, okay? So we can easily find the volume of the sphere because we know the radius of the sphere is 2 centimeters, okay? Now the volume of the cone is expressed in terms of the radius, which we do have is radical 3, and the height. So the height here is actually the distance from A to C, and that's the one we don't have, okay? So how do we find the distance now from A to C? Well, you want to look at triangle ABO here, okay? So there's a piece of information in the problem that's going to help us, okay? So it says here, that the scoop is tangent to each line containing the slant height, okay? So what that means that this part over here, that's the slant height, is tangent to the circle or to the sphere in this case. So what does that mean when it's tangent? Well, it means that we have a right angle here somewhere, that the tangent and the radius do create a right angle, okay? Okay, so now we have another right triangle. As a matter of fact, it's triangle ABO that is a right triangle. Okay, so now we can use the right triangle altitude theorems that we have developed to solve this problem, okay? As a matter of fact, as you remember, if you have a right triangle like this, okay, let me actually draw a better right triangle here, like this, and you draw the altitude, you remember that we can here apply the geometric means. For example, that the height of this triangle is the geometric mean between the left piece A and the right piece B of the hypotenuse itself. And that's exactly what we can use here, okay? So just imagine that instead of having A and B and H, we have the following points here. This is B, this is O, and then we have A over here, and this is C, okay? So we know that the distance from O to B is 2. From B to C, the height of this triangle is radical 3, okay? And now we figured out what OC is, which is 1. So we want to find this distance here. That's the distance we're trying to find. Okay, so in order to do that, we can set up a geometric mean, okay? And as a matter of fact, as you remember, the altitude, so let me write this. The altitude BC is the geometric mean between the left piece, AC, and the right piece of the hypotenuse, which is OC, okay? So our goal here is to figure out AC, or to solve for AC, and then substitute everything in it. So let's do that really quick. So here we end up with BC squared equal to AC times OC. And all I did here is cross multiply, okay? According to the theorem, the product of the means is equal to the product of the extremes. Okay, so now we're going to solve for AC, okay? And AC is equal to BC squared divided by OC. So the good news here is that we do have BC and we have OC. So let's substitute that. So BC is radical 3. And luckily we square it, so we end up with a nice whole number. And OC is just 1. So we end up with an AC value, which is equal to 3, okay? So keep in mind that this number here represents the height of the cone, okay? So that's great because we have the height of the cone, we have the radius of the cone, and the radius of the sphere, and we can just substitute it in this formula here and obtain the result, okay? So let's first write the volume of the sphere, okay? So the volume of the sphere, we know it's 4/3 pi r cubed, okay? So all we need to do is substitute here. So volume of a sphere is equal to 4/3 pi times, so we know from the problem here that the radius of the sphere is 2. So we take 2 centimeters and cube it, okay? So if you do the math here, you should get a volume for the sphere to be equal to 32 pi over 3. And that is centimeters cubed, okay? All right, so the volume of the cone, on the other hand, is 1/3 pi r squared times h, okay? So that means that the volume of the cone is just equal to 1/3 pi times, so the radius of the cone is just radical 3. So we square that times the height. And we figured out the height here to be 3 centimeters, okay? So let me add centimeters here. So we're going to write that in, times 3. Obviously, we're going to put the dimensions and swell when we're done, okay? So here, a third and 3 cancels. So we actually conveniently end up with a volume for the cone to be equal to 3 pi centimeters cubed. Okay, so that's great now, because all we need to do is subtract the volume from the cone from the volume of the sphere, okay? So that means that the volume, let's call that volume, let me see, here it says, here we want to find how much he ate, okay? So let's call it volume 8 is equal to the volume of the sphere, which is 32 pi over 3 centimeters cubed minus 3 pi centimeters cubed, okay? So we're going to find the common denominator here, which is 3. Okay, let me actually write the pi a little nicer. There you go. And we're going to subtract 9 pi over 3 centimeters cubed, okay? All right, so that means that the volume that Dennis ate of the ice cream is simply 23 pi over 3 centimeters cubed. And that is the answer to this problem here, okay? So the answer is 23 pi over 3 centimeters cubed. It is always preferred that you leave your answers exact in terms of pi and also as a simplified fraction, okay? Okay, so this is basically today's lesson on how to deal with combined solids, how to find the volume and surface areas. I would like you to please finish homework 99, okay? This homework is actually due on Thursday. If you have any questions, please feel free to email me or post a comment to this YouTube video. Other than that, have a great day.